Okay, good morning, everybody. Welcome to the IvS seminar. Let me just really briefly introduce Alex. I guess you've seen the announcement already. He's a professor at Vanderbilt. And so he has a history being one of the good guys in high energy theory since he was a student of Andrew Strominger, but then he's left for greener pastures in astro and relativity. And so he's going to talk about the photon ring. I'm not going to tell you what that is. He is. But I do want to impose on you the seriousness of which he is interested in the photon ring. And I think his license plate in Tennessee really shows that he's serious in every aspect of his life to talk about the photon ring.
Okay. Thank you for the personal touch, Daniel. Let's see if this works. Okay, good. Well, thank you for the invitation to speak here. It's a pleasure to visit KU Leuven for the first time and to see some familiar faces and many new ones. So today I'm very excited to tell you about the black hole photon ring, which is something that I think nobody really talked about up until about 5 years ago, but which is now becoming an increasingly important part of studies of black holes, both in theory and in observations. And what I'll do today is assume you haven't heard about it. So if you know what it is, there's going to be some review. And if you don't, then you've come to the right talk. And I'll spend most of my time explaining the theory of what this photon ring is, what produces it, why it's interesting, why it should matter, why we care, and how we're going to see it. And I should say that this is now a field with connections direct connections to observations, with the NASA mission proposal that is now in pretty advanced stages of development. So everything is changing every month, but I'll tell you a little bit about it at the end. And I'm happy to hang out afterwards and answer any questions. And I should also say, I know many of you are astronomers and others are high energy theorists, and my goal is to speak to everyone. And I'd rather go through less material but be completely understood than move very fast and lose people. Okay, so without further ado, I'd like to start every presentation on the subject with this video, which has been produced by these collaborations listed at the bottom here. The key point is, this is a video that is made with real images. None of this is simulated. These are all real observations that have been taken by various instruments over the past several decades. So you look to the sky in the direction of Virgo, and you start to zoom in, and you zoom in, and you zoom in. There's this galaxy called Messier 87, which is 50 million light years away, has a very powerful jet, this collimated light beam, that's been observed for many, many decades now. And we believed for a long time that at the core of this beam, the central object that powers this jet is a black hole. And this was first resolved in 2019 by the Event Horizon Telescope, a collaboration that released this first image of a black hole, which I'm sure many of you have seen. So this is the first image. And if you, like me, went to maybe some of you watched the announcement by the NSF when this image was first released. And the first two questions by journalists were, it's kind of blurry. That was the first question. And then there was some political answer. And then the second question was, yeah, but can it get a little bit better? And of course, this is a tremendous technological achievement because this black hole is bigger than our solar system. It weighs 6 billion solar masses, but it's so far away, 50 million light years, that it has a tiny, tiny size in the sky. So its angular size in the sky is the same as an orange on the surface of the moon as seen from the Earth. So to take this picture, it's like saying, okay, there's an orange on the moon, take an up-close shot. And it's really amazing that we could even get this picture at all in the first place. But of course, now that we know that this can be done, in some sense it becomes an engineering problem. And it's pretty clear that one way or another, in the next 10 years, 15 years, we're going to get much sharper images of this black hole and also Sagittarius A star, the black hole at the center of our galaxy. And unfortunately, probably we won't get much sharper images of any other sources in the near future, because those are the biggest ones in our sky, and all other black holes are much, much smaller. So these are the two to focus on if you want sharp images. So if you're a theorist, this immediately raises a question, which is, okay, well, what do we expect to see, really, when we have high resolution? And to answer this question, a lot of our colleagues who do plasma physics have developed this theory called general relativistic magnetohydrodynamics, or GRMHD, which is a fancy word to describe the equations that govern charged plasmas, so charged particles, flowing in the background of a curved space-time, such as the Kerr geometry that describes black holes. So it's a very complicated theory, but you can simulate these plasmas on supercomputers. It's very expensive, but the Event Horizon Telescope collaboration has a number of such simulations in their library. There's about 40 or 50 of them. And each simulation is a movie of the source, of course a simulated movie, and then you can ray trace the simulation to obtain many images, of which this is one, but there are millions of images in that library. And what's really striking about it is that all these images actually are dominated by the same striking feature, which is this bright ring of light. Now, this is the photon ring, and I'm going to explain why it's there. But this statement that across millions of images of different simulations with different astrophysical conditions, different initial conditions, different plasmas, different magnetic fields, you can vary the conditions across a wide range of parameter space. And no matter what you do, at the end of the day, in your images, you always get this ring. So let me first say that the black hole can be seen in this image because there's a dark patch. So this dark patch really is the imprint of the event horizon. It's completely dark because there's a black hole there. This is gas that's flowing onto the black hole, the accretion flow, and it radiates basically all the way to the horizon. But a little bit farther away, you have this distinctive stamp, which is the stamp of the black hole's strong gravity. That's the photon ring. And what I'm going to explain to you in detail over the next 20 minutes is that this ring is always there because the black hole is always there. And it's the part of the image that belongs to the black hole itself, not to the circulating plasma around it. And the way you should think about it is that whatever source of illumination you put around the black hole, that's going to create some image which is going to show you whatever is around the black hole. And that we don't really know. That's astrophysics details. But provided that there is some source of illumination, some plasma or something else, the presence of a black hole will lens the emission from the source, and some of the light will tumble around the black hole and get lensed into this characteristic pattern of the photon ring. And today we have very sharp predictions for the structure of this ring. And actually I want to give a shout out to Daniel Meyerson here, who I think has done the best work so far of understanding how this prediction is modified beyond the Kerr black hole of general relativity. Okay, so this is the general picture, and now let me get into some details, although there won't be too many equations. So I'd like to start the story really near the black hole, deep in the geometry. And there's a region of space-time around a Kerr black hole, which is called the photon shell, which is not so well known, but has become more and more important as we focus on observations of black holes. And this turns out to connect not just to black hole images, but to quasi-normal modes as well, as I'll mention in a little bit. So what is this region? Well, if you look at the r theta plane around a black hole, everyone knows that a black hole has an event horizon, which is depicted here by this black disk. What is less obvious is that outside of the black hole, there's this region, which is depicted here, in which gravity is so strong that it's possible for light to be deflected so much that it actually orbits around the black hole at fixed radius. Now, it doesn't mean that any photon emitted here has to stay in the photon shell at a fixed radius. In fact, generically, if you're sitting here and you shine your flashlight, the photons that you emit will fall into the black hole, or maybe they'll escape to infinity. But what's special about this region is that if you stay here with your flashlight, it is possible for you to aim your flashlight just right to load photons onto an orbital shell where they'll stay captured in principle forever. You can't do that anywhere else in the geometry. So the photon shell is a region from which light can still escape, and generically, it doesn't stay there, but if you aim just right, light can be captured on one of these shells. And Leo Stein is a relativist who has a website, due2symmetry.com, with this really cool 3D Java applet. It's interactive, you can play with it, it's very fun, I encourage you to do it. And this is a screenshot from that, where you see one of these orbits. Now, these orbits are completely determined by the geometry, so they depend on only the mass of the black hole, its spin, and then there's a range of radii within the photon shell where you can have this behavior. But notice that for almost all radii in the shell, the bound photon orbits don't actually fill out a sphere around the black hole, but rather they go around the black hole in angle phi, but they bounce up and down in theta. So in classical mechanics, this is called vibration. They're just bouncing up and down. And throughout this talk, I'm going to talk about photon orbits. And when I say a photon describes one orbit, I mean one periodic oscillation of its theta polar motion, going from the bottom of the shell to the top and back down. And really, the relevant thing to describe black hole images is going to turn out to be half orbits, and a half orbit just means one bounce from the bottom to the top, or vice versa. So I hope that's clear. If there are any questions about half orbits, now's the time. Okay, so there are 4 quantities that are intrinsically defined in this geometry that are going to turn out to control the lensing behavior of a black hole. So these are the only 4 quantities I'm really going to describe in detail, but it's important to take some time to do that. So the first 2 are quite simple to describe. If you pick one orbital radius in the photon shell, you can ask, in the time that it takes for a photon to do a half orbit, so to go from the bottom to the top, what's the coordinate time elapsed, delta t? So how long does that take? And that we call tau. And of course, these orbits, you can see from this image, they're not closed. They actually sweep out these shells ergodically. They explore everything. There's a measure 0 set where they actually close in on themselves, but generically, they sweep out the whole shell. And so when they go from the bottom to the top and back down, they don't come back to themselves in angle phi. And delta is the azimuthal angle swept per half orbit. So those are 2 parameters, delta and tau. Basically, how long it takes for a polar half orbit and how much you go around the black hole when you do that. Is that clear, or any confusions? Okay, good. And the next 2 are a little bit more complicated to explain. Let me focus on mu first, and then the next slide will describe gamma. So if you have a Schwarzschild black hole, you know that the event horizon is at r equals 2m. And it turns out that you don't have a photon shell, you have a unique photon sphere where light rays can be orbiting the black hole, and that's at r equals 3m. Now, if the black hole spins up, the effect is that the horizon shrinks in these coordinates, which are the standard Bohr-Lindquist coordinates, but the photon shell thickens. So if you're in Schwarzschild, you only have this white circle, which is the unique radius in the photon shell where light can orbit with 0 angular momentum, and 0 angular momentum is necessary to be able to pass over the poles. So those are the only orbits that can really truly explore a whole sphere. But orbits within this white shell, the photon sphere, have to co-rotate with the black hole because the photons have positive angular momentum, so they're on prograde orbits. And photons outside of it have to counter-rotate with the black hole because they have negative angular momentum and they're on retrograde orbits. So these photons in here, they're spinning with the black hole, and the photons outside, they're going opposite with the black hole's rotation. And mu is the signed inclination of the orbit. So notice that at the innermost radius of the shell, actually these oscillations in theta, they shrink, they shrink, until eventually the last circular orbit that you get is a circular equatorial orbit, and it's prograde. It's going around with the black hole. And so the maximal angle of the oscillation is pi over 2, which means sine of pi over 2 is 1. So we can assign an inclination of 1 to this innermost orbit. As you go from the innermost orbit to the zero angular momentum shell, the signed inclination, so theta grows from theta goes from pi over 2 to 0, which means the sign decreases from 1 to 0. And then as you go outwards from here to the outermost radius in the photon shell, where you have, again, a circular equatorial orbit, but now a retrograde one, sign again grows from 0 to 1, but because the photons are counter-rotating, and we want to distinguish the two halves of the shell, we put a minus sign there. So mu goes from +1 here to 0 on the white shell to -1 at the other extremity. And so we can think of the orbital radii in this shell as being parametrized by mu, which is basically the inclination going from +1 to -1. And this is a 1-to-1 bijection. Okay, so this one was a little bit more complicated, but does that make sense? I see nods, happy nods. Question? Very good question. So if you look at this white shell, the photons that are bound there have zero angular momentum in the sense that the geodesic momentum, p mu, if you dot it with the killing vector d phi, you get p phi, the angular momentum, and it's 0. That doesn't mean that they're not co-rotating, because the Kerr metric is not diagonal. So p lower phi is the angular momentum, it's 0, but then when you raise the 4 momentum with the non-diagonal metric, you get a non-zero p upper phi. So the photons can be co-rotating even if they have 0 angular momentum, and the physical interpretation of that is that there's a frame dragging effect. So they're not rotating, but the space-time they're in is rotating around with them. Yeah, okay, once you get into the details, it rapidly gets very complicated. I should say here I'm showing a black hole of near maximal spin, so it's got 94% of the maximal allowed spin, which means the shell is very thick, and as you push up the black hole to the maximal allowed spin, the horizon shrinks to r equals m, so from 2m in Schwarzschild with no rotation to m at maximal spin, and the shell thickens from the photon sphere at 3m in Schwarzschild to a very thick shell that goes from m, where the horizon is, basically to 4m. Okay, so that's the geometry of the photon shell. It's the place around the black hole where light rays can be orbiting around it. And there's these critical parameters, of which I've described 3, delta, tau, and mu, that are completely determined by the space-time geometry and the behavior of these orbits within the photon shell. So this is a purely geometric slide. There's no lensing, no images just yet. We're going to get up to that, but this is the fundamental physical picture that we need to keep in mind. Okay, before I move on, let me explain the final parameter, gamma. So it turns out that light doesn't like being trapped, and so these orbits, they're bound, but they're unstably bound. So they really sit at the peak of an upside-down potential. It's like an inverted harmonic oscillator. And what that means is that if you take a photon, which is aimed just perfectly right to be loaded onto its shell, but now you give it a little perturbation, a tiny little kick, delta R naught. By studying the equation, the geodesic equation in the Kerr spacetime, and in particular the geodesic deviation equation, which is also known as the Jacobi equation, you can show that if you give this photon a tiny little kick, it's actually going to exponentially deviate away from its orbit. And in fact, the radial deviation from the orbital shell where it starts will grow exponentially fast in each half orbit. So it's going to go off, and then bounce, and in every bounce, it's actually going to exponentially move away. Until after n turns, it's going to be the initial displacement multiplied by e to the gamma n. And this gamma is a Lyapunov exponent that governs this rate of orbital instability. And again, is only a function of the black hole parameters, the mass and the spin, and the orbital radius. Is that clear? Any questions? Okay, so just to tell you where we're going, now that we've understood the structure of orbiting light in the photon shell, we're going to study light that's not quite captured, but nearly captured. We're going to study nearly bound orbits. And it turns out that those can escape, and they can escape to our telescopes, and they're the light rays that are responsible for the photon ring effect. So to explain this, I need to describe black hole imaging. And so very briefly, there's a lot of subtleties hidden in this plot, but Bardeen in 1973 defined Cartesian coordinates, alpha and beta, on the image plane of a distant observer far away from the black hole. And you should think of the origin as the direction along the line of sight to the center of the black hole. We're in curved spacetime, so coordinates are a little bit ambiguous, but you can make this precise. So you should think of this as a coordinate system on your sky where the origin is pointing to the black hole. That's the line of sight. And beta is the projected spin axis of the black hole onto the plane perpendicular to the line of sight. So beta is the image of the spin axis. And once you know that, then alpha is the perpendicular coordinate, and now you have a coordinate system. And the really interesting question to ask is, suppose I look to the sky, and there's a black hole there, and I have my little laser pointer, and I shine photons backwards into the geometry towards the black hole. The key question is, what is the eventual fate of these photons? And it's clear intuitively that there are two possible behaviors. So if I aim my flashlight towards the black hole, then the photons will travel to the event horizon, cross it, be absorbed, and never come back out. That's the familiar story. So in other words, if I aim around the origin, the light that I send towards the black hole will get sucked into the horizon. And that's it. On the other hand, if I aim very far away from the black hole, so the black hole is there, but I'm pointing over there, the light ray will never fall in. Now, it might experience some gravitational pull from the black hole and be deflected. It'll swerve a little bit, but it'll eventually go back to infinity. So there are two qualitatively different behaviors, depending on where you shine your light towards the black hole. There's a region of photon capture, which is the apparent cross-section of the black hole. That's the set of directions in your sky where light rays end up crossing the horizon. And then there's a region of photon escape, which is the region where light rays maybe get deflected but go back to infinity. And now the question is, what's the boundary between these two regions? And Bardeen in 73 derived it. It turns out there's a simple analytic formula for this boundary. It's called the critical curve, and I showed it here as this red curve. And it turns out that if you aim a light ray exactly, precisely on this infinitely thin mathematical curve, well, it can't be absorbed by the black hole, and it can't go to infinity. It's neither captured nor escapes. So what can happen? Well, it turns out that those light rays will actually come in from infinity and then asymptote to one of these bound orbits in the photon shell and basically be loaded on the shell and orbit forever. So the critical curve is the image on a distant observer's image plane of the photon shell. That is to say, it consists of the directions in which you can send light rays in such a way that they asymptote to bound orbits around the black hole. And now you can ask, okay, but what is the meaning of the angle around the critical curve? And it turns out that which angle you shine your flashlight at around this curve will determine which radius within the photon shell you load your photons on. And that should be really, really, really surprising, okay? Because if you look at a star in flat space, when you look around the star in the image, you're seeing around the star in the geometry. What I'm telling you here is that as you look around the black hole in the sky, you're not seeing around the black hole in phi. You're actually changing the radius, the distance at which you're looking to the black hole within the photon shell. And that is a signature of the warped nature of space-time in your face. Okay. So if I aim my flashlight at this angle, it's going to emit photons that come in from infinity and are loaded onto a photon shell at small radius. But if I aim my flashlight farther out, so still on the critical curve, but here, then the photons will be loaded onto a different orbital shell farther out. So the angle around the image doesn't correspond to different angles phi around the geometry of the black hole, but different radii. And as an aside for high-energy theorists, there's very tantalizing connections to holography, and we've written a couple of papers about that I'm happy to talk about later. Okay, so this is a bit of a rabbit hole. It's very fun, but you can spend forever thinking about the intricate properties of light in this geometry. So let me give you the bare bones summary of what I want you to take away, and that's enough to understand the complete details of the photon ray. Yes? Yes, very good. So the black hole spins into the page and then back out. Yes? Yes, very good. That is exactly correct. So, okay, I'm going off script, but this is radius. This is the shape of the potential near the photon shell. So if you aim your flashlight here, outside of the critical curve, effectively its energy is below the peak. So it comes into the geometry, reaches a minimum radius, and then turns back around, which physically means it swerves. So it reaches a turning point in radius, and then it goes back out to infinity. If you aim your flashlight within the critical curve, then it just falls into the black hole. And this critical curve corresponds to the light rays that are aimed exactly at the top of the peak, such that they just end up there. But of course, these orbits are unstable. That's why there's a Lyapunov exponent. And another way to say it is it's infinitely hard for a light ray to be perfectly bound, because you have to aim infinitely precisely on this perfectly thin mathematical curve. And you're actually getting to my next point, which is that if I don't aim perfectly precisely on the critical curve, but I aim at a small perpendicular distance d from this curve, then as long as d is non-zero, the photon I shoot back won't be captured forever. But if d is very small, it'll actually come in from infinity, skirt one of these orbits. In particular, if I'm at, right here, then the photon is going to come in and skirt the bound orbit that corresponds to this angle around the critical curve. Is going to orbit around it for a long time, and then eventually will fall in if d is slightly negative, or eventually go back out if d is slightly positive. So there are critical rays which asymptote to bound orbits, and there are near critical rays which have small deviation d from the critical curve, and these near critical rays correspond to nearly bound orbits that spend a lot of time orbiting around the black hole in the photon shell before eventually falling in if they're slightly within the critical curve with negative d, or eventually escaping if they're slightly outside the critical curve with positive d. And because of this terminology, the previous parameters, gamma, delta, tau, are often called critical parameters. And I should say here that there's two reasons why we use the terminology critical. One is because these are properties of the critical rays that appear on the critical curve, but there's also a deeper reason, which is that this photon shell is associated with an emergent conformal symmetry that I won't have much time to discuss today, but I'm happy to talk about it afterwards. And the emergence of a conformal symmetry is the modern definition of critical phenomena. And that's another reason why we like to use the word critical. I'm happy to talk to you about that afterwards. Okay, but the picture I want you to take away is that a black hole actually is an omnidirectional lens. It has this photon shell, which is this giant tumbler in which light can come in from every direction, zoom about and then come back out in every other direction. So a black hole is like an extreme lens that takes light from everywhere and sends it back out to everywhere else. And the consequence of this is that if you have a single source around the black hole, it can actually connect to a single observer along different paths, along different light rays. In fact, you can prove mathematically, it's not very hard, that in a Kerr black hole, in the background of a black hole spacetime, if you pick any two spatial points, they will be connected by infinitely many light rays. And in fact, you can label these light rays, these different light rays, by the number of times they orbit around the black hole. So there are infinitely many of them, but it's a discrete infinity, which is labeled by the orbital number. And to explain this in full detail, I'm going to focus on a simple case. Now, I should say we understand it, of course, in complete analytic detail in every configuration, but for the purpose of this seminar, I'll give you the simplest example, which is imagine an equatorial disk observed by an observer who sits on the spin axis of the black hole. So in the next 2 minutes, I'm going to describe this setup in detail, and you'll see how everything falls into place. And if you want to hear about the more generic, complicated case, I'm also happy to describe that afterwards. So suppose you have a point source in this equatorial disk. These two light rays are actual light rays in the Kerr geometry that connect to an observer at 17 degrees from the spin axis of the black hole, but the observer is infinitely far away, which is why these light rays don't appear to converge yet, but they do once you go very far out. And so the blue light ray shoots down under the disk, but then gets pulled by the black hole and slingshot back up. It crosses the equatorial disk at another location and then goes up on its way. And then this green ray actually shoots up, but then goes under the black hole and then it comes back out before eventually reaching the observer. So the blue ray does 1/2 turn around the black hole, 1/2 orbit, and the green ray does 2/2 orbits because it shoots up and then down and then back up. And it turns out that every source in this setup connects to the observer along infinitely many light rays that can be indexed by the number of half orbits. Okay, so this is the most scary slide. I'm going to walk you through it slowly, but it's putting everything together. So let's first focus on the right-hand side. This is just another cartoon picture to illustrate what I just told you in words. So we imagine that we have our little eye here, the observer, that sits on the spin axis of a black hole, of course, very far away. And we're going to consider an equatorial disk around the black hole. And based on what I just told you, you expect to see actually infinitely many images of the disk, starting with a direct image from light that just goes directly off of the disk to the observer. That's the direct emission that doesn't do any half turns around the black hole, so we call it n = 0. And that's what you would see if this were a star. It's the only thing you would see. It's just basically an image of the disk. But if this object here in the center is a black hole, then in addition, you're going to have these light rays that skirt the photon shell, and in particular, you'll have another image of the disk from light that goes under, does 1/2 orbit and goes away, and then light that goes up and then back down, does 2/2 orbits, and then escapes to the observer, and so on and so forth. And now I'm going to switch to this color wheel, which makes a very important point. Whatever the n = 0 image is, depends on what the actual source is. It just shows you what's around the black hole, and that you can predict just from general relativity. However, if you know what the nth image of the disk is, the n + 1th image can be completely predicted from general relativity because it's just a mirror image of the emission lensed an additional time around the black hole. And this color wheel illustrates this relationship. So imagine that we're in the setup again, and this black curve is the critical curve that I just described previously, where it was red, now it's black. So this is the image of the photon shell. And imagine that my source is a disk, which is actually a color wheel. Of course, no astrophysical disk is a color wheel, but this is useful for illustration purposes. And suppose this is the mth image of the disk that I get from photons that did m½ orbits. Then we can completely predict what the m + 1th image will be. And it's basically a lensed image of the same thing, but changed in 3 different ways. So let's focus here on this lower panel, which corresponds to a non-rotating Schwarzschild black hole. So in this case, the color wheel will be demagnified, it will shrink, it will be squeezed towards the critical curve by an amount e to the minus gamma. And for Schwarzschild, the Lyapunov exponent gamma can only take one value, which is the value associated with the unique photon sphere, and that value is pi. So this is exactly e to the minus pi, which is about 5%. So the first effect is the color wheel gets squeezed by a factor of 20. And that makes sense because I just told you before that you have to aim exponentially closer to the critical curve to do an additional turn, because it's exponentially hard to do more turns. So the image from light that did an additional turn has to be aimed exponentially closer to the critical curve. And that exponent turns out to be exactly the Lyapunov exponent that governs the instability of the photon shell. So that's the first effect. It's the demagnification effect. The second effect is that the color wheel turns. And you can see this here because the n=1 image actually goes under the black hole. So if you had something which on the n=0 image was on the right side, now it's going to appear on the left side. And if you think about this in 3D, it just means that the whole image is rotated by exactly half a turn. So it turns out that the image rotates exactly by the angle swept by an orbit as it does a half turn, which you can compute in Schwarzschild is exactly pi, or 180 degrees. And finally, the image is time delayed. So now if your source is fluctuating, so you have a movie rather than a static source, you're going to see the m+1th image be time delayed by exactly the time it took for the light ray to do an additional half turn, which was defined to be tau a few minutes ago. So in other words, what you expect to see is a set of images of the source, all of which show you the same picture of the main emission, but successive images are demagnified by e to the minus gamma, rotated by delta, and time delayed by tau, where gamma, delta, tau are critical parameters defined intrinsically within the photon shell of the Kerr geometry. And what that means is that these parameters, well, they're really functions of mass, spin, inclination. They're really, you should view them as fundamental constants of nature that are predicted by general relativity and that are observable, because we can, in principle, measure them by comparing the successive images of a source. Yes? Yeah, so the photon shell exists for a black hole and only for a black hole. So the reason is only a black hole is compact enough to lie within its photon shell. So if you have a neutron star, of course it's described to leading order by the same geometry, but it won't be compact enough for the surface of the star to lie within the photon shell. So in other words, the star will include its photon shell, and so there can be no such effect. Now there's this theorem called the Bookdahl theorem, but it's not powerful enough to make this statement. And in fact, people have come up with exotic quark stars, boson stars, which are exactly designed to be compact enough for this to happen, but I don't believe such things exist, really. So it's hard to make it rigorous as a mathematical statement, but I'm pretty convinced it's true. I think only a black hole can do this. And then you have to make various assumptions to prove this. Okay, and of course this was the Schwarzschild black hole, but now you can ask about the effects of spin. So the mass of the black hole just sets the scale of the critical curve. A bigger black hole has a bigger image. And the effects of spin can be summarized in these 2 panels. So as you spin up the black hole, the photons that orbit around it get frame dragged. So delta increases, and so the color wheel rotates more until you reach maximal spin, and the rotation is almost exactly 3/4 of a turn. However, these orbits are more stable, and so the demagnification factor is actually larger. So the images get less squeezed in. And interestingly, the time delay is roughly always the same. It's always about 15M. So for M87, M is about 9 hours when you convert to units of time. And so 16M is about 6 days. So if you looked at M87, you'd expect to see light echoes on a characteristic time scale of about 6 days. I have much to say about that too, but ask me later if you're interested. And lastly, I would like you to take away these equations. These are the last equations, really, that I'm going to explain in detail. These are obtained by solving the null geodesic equation in Kerr in the large n limit, where n is not the QCD n, but the orbital number n. And you can prove that in this configuration, this is an exact statement at large n, which is to say, if the nth image appears at a perpendicular distance dn from the critical curve at angle phi n around the curve and at time tn, then the next image will appear at distance, angle, and time n plus 1 that are related in this way. And this is a statement that follows purely from general relativity, that is to say, purely from the geometry of a black hole and its slanting behavior. Okay, so now let me put everything together with a nice movie. So when you look at a black hole, there's going to be some matter around it, some hot gas that's going to radiate light. Most of this light will follow n equals 0 trajectories that are weakly deflected and just show you the direct image of the main emission around the black hole. But on top of that, you're going to have some light rays that are aimed just right to skirt the photon shell and do 1/2 turn inside of it before being lensed back towards the observer into this characteristic photon ring shape. And this is the n equals 1 photon ring. But some fraction of the light will be aimed exponentially closer to this photon shell, and it will do an additional turn. So you have to aim better and better in phase space now, but some of the light rays can do 2 half-turns, and then they'll get lensed into an exponentially narrower ring, which is the n equals 2 photon ring. And of course, this is electromagnetism, so we have superposition of light waves, and the net image is the sum of all these layers. That is to say, the n equals 0 background layer, which is just an image of the stuff around the disk. And superimposed on top of that is gravity's stamp, which consists of these photon rings labeled by n, each one of which is a lensed image of the main emission, forming this structure that is completely predicted by the Kerr geometry. And these are real rays that you just saw. And we hired a studio to make the animation, but the rays are real. Yes? What a great question. Step into the next slide. Yeah, so everything I told you so far could be sci-fi. We've never tested this. Okay, it follows from the equations, but you shouldn't believe things until you check them. Now, luckily, we have sort of an intermediate check of sorts, which is to go back to these GRMHD simulations, these state-of-the-art simulations that we described at the start, where there's a lot of complicated details, but they don't assume what I just told you. It comes right out of their simulations. And so what you see here on the left-hand side is the image I showed at the start, which is actually time averaged. It's a time average over many images of a movie of a state-of-the-art simulation of M87. And now you can take cross-sections of this image. So you can take a horizontal cross-section, which is shown here in red, and you can take a vertical cross-section, which is shown here in blue. And you can see these spikes. So the spikes are the photon ring effect. And now we can zoom in on the spikes. That's these bottom panels. This is the total intensity that you see, but we can decompose the contribution to the total intensity by the photon half-orbit number n. So you can see that there's an n equals 0 background. That's this shoulder of the emission. And then on top of that, there's a first spike here, which is the n equals 1 emission. And then on top of that, the n equals 2 and the n equals 3. And I should say this qualitatively matches and quantitatively matches the predictions from the previous slide from analytics. These things get squeezed by about e to the minus gamma is 10%. They get rotated, time delay, et cetera, et cetera. And George Wong, who did this, said that you could see at least up to n equals 6 in the simulations, and then things get exponentially hard to measure. And so to answer your question now, the intensity in each layer is roughly the same, because the way these images are computed is via radiative transfer. which means you shoot a light ray back into the geometry, and whenever it intersects the hot plasma, the emission region, at every point, at every little increment of the light ray through the emission, you update the number of photons loaded onto the ray according to the local source emissivity. So, the ray crosses the matter is hot, you can load particles onto the ray, so on and so forth. And you integrate that along the path. But basically, each time you do an additional orbit, you pass through the same emission region, because you're just bouncing up and down in the shell. So you pass through the same emission region, the same angle, and so you pick up roughly the same photons, the same contribution. And that's why the intensity loaded through each pass is the same. That's what you expect from analytics, and that's what you see in numerics. In other words, the height of this peak is roughly the same as the height of this peak, is roughly the same as the height of this peak. But of course, because the area under the curve gets squeezed, there's exponentially less flux. So in this image, about 90% of the flux is in the n equals 0 layer, and about 9% is in the n equals 1 layer, and about 1% in the n equals 2 layer, and so forth. Okay, adding up to 100, of course. Does that make sense? Yeah, so let me say it again. There's a hot plasma of charged particles that are evolving around the black hole, probing its strong gravity, but also exerting forces, electromagnetic forces. So it's magnetohydrodynamics in a curved spacetime. That's a very costly thing to simulate. Once you have that simulation, you can ray trace it, which means you set up your image plane, and then at every observing time, and for every pixel on your screen, you shoot a light ray back, and you ask along the light ray, wherever it intersects the hot matter, how many photons are loaded on, and you count that, and that's how you make these images. And the details of this go under the name of radiative transfer. It's like there's a whole graduate student textbook in astronomy, Lightman and Rybicki. It's pretty messy actually. The details really matter. Yes. So this is a simulation at 17 degrees from the spin axis. But you're right, there's an offset that goes roughly like twice the spin times the sine of the inclination, 2a sine theta. And actually, this offset between the darkness, the brightness deficit at the center, and the bright ring is a probe of spin because of this dependence. Yeah, so I won't have much time to get into this today, but of course, this is a good time to tell everyone we're actually going to measure these things. For sure. It's just a matter of time. We're trying to make it happen in the next 6 years with this NASA mission proposal that is due in a few months. I think there's a really good shot that it's going to come through, but I have no doubt that human beings are explorers, and these are the two biggest black holes in the sky. Unless we all destroy each other first, there will come a time when we measure this. It's just a matter of when. And I think we're going to see all of these things. And of course, to get hundreds of millions of dollars from NASA and the astronomy community, you can't just sell this as, we're going to probe GR in the strong field regime, because they don't care. But they do care about measuring black hole spin, because it turns out that there's really no good method of measuring black hole spin with high precision. There's some constraints you can put from gravitational waves that are getting better and better. But of course, those are always for stellar-sized black holes in a dynamical regime. This is the pristine gravity of a static black hole that's supermassive. And for such black holes, there have been various methods developed for inferring spin from electromagnetic emissions. They go under the name of continuum spin fitting method or X-ray reverberation method. And they're all kind of made up and hokey, in my opinion. And I'm happy to explain why. And I think this is really the only chance you have at measuring spin in an astrophysics-independent way is to actually hang your hat on something that doesn't depend on the astrophysics, which is the geometry of the black hole. Because the other methods assume that you know exactly what you're looking at around the black hole, which in practice is not the case. Yes? Yeah, so this is not going on YouTube, right? Yeah. Yeah, it's a political question. I'm happy to talk about this sort of when I'm not being filmed. But let me just say, the first order approximation, the things that NASA really cares about are the things that the public really cares about, and that's aliens. So whatever you try to do, if you're going up against aliens, you're going to lose. And every big NASA mission searches for aliens in some form. I mean, they have coded words like, origin of life and looking for water lines, but it's all aliens. So that's like the big thing to do, okay? And then if you're not doing aliens, you're trying to do some kind of scientific measurement. There's like 5 decades of this huge astronomy community growing around NASA that has their own sort of internal goals. They're interesting goals, but this is kind of out of left field, and they're just pushing for more of what they've been doing, which is normal. So it is a bit of a challenge to try to propose a NASA mission that probes strong field gravity, which is not something they've done before. And my model of this situation is that the community of astronomers that are immediately adjacent to NASA, they care about X-ray polarization and basically a lot of the things they've been doing for the past few decades. And I think as soon as you step away from that to the larger community of people like Daniel who are interested in gravity, all of a sudden this looks way more interesting. And luckily, I think once you get to the wider public, 5-year-old kids nowadays know about black holes and think it's really cool. And so we've got that going for us. But it is a bit of a challenge how you convince the astronomy community in particular to be interested in this. And I think spin measurement is one way to do it, because there is, like I said, I think no really good way so far of measuring spin with electromagnetic emissions, and this will do it. And the Nobel Prize was given for the measurement of the mass of Sagittarius A star. And as I'm going to get to in a couple of minutes, we're going to be able to measure the spin of Sagittarius A star. So, measuring the spins and masses of many black holes is maybe not that interesting once you've done it 100 times. But when it's the first time you're doing it as a proof of principle, it's an important benchmark. And then the next milestone is when you've done it for 1,000 sources, and now you can do statistics and black hole population demographics, and that gets really interesting, again, for other science reasons. Okay, so let me summarize everything I've told you about the theory. It's a prediction from general relativity that within a black hole image, there ought to lie a thin ring, the photon ring, which is actually composed of a stack of self-similar subrings. These subrings are self-similar because each one of them is a lensed image of the same thing, of the source around the black hole, and you can label these rings by the number n of photon half-orbits around the black hole. And the structure of these rings and the relation between the images is governed by the lensing behavior of the curved black hole, which is completely characterized by these 3 measurable parameters, gamma, delta, and tau, which, as I explained, controlled the relative demagnification, time delay, and rotation of successive images. And these photon subrings, they converge to this critical curve, which has a very specific shape that's analytically predicted by the Kerr geometry. And you should think of as the strong gravity of the black hole putting a stamp on the image. Now, because I wanted to explain everything in detail, I chose to explain this in image space, because we have our powerful visual intuition to help us. But of course, the way we actually image these black holes is not by taking images the way you see with your eyes or the way your iPhone snaps pictures, but rather using interferometry, which actually is a very complicated technique that could be a whole hour to explain how it works, but you've probably heard about it, hopefully. The key point is that it's a technique that allows you to see the image in Fourier space. So you're actually seeing frequencies of the image or characteristic notes within the image. And the key idea for this is that just like the ring is a very sharp feature in image space, it's like all of a sudden this like sharp, narrow brightness increase, it's also a sharp feature in Fourier space because you have this large change in the intensity. There's a steep gradient, which means high frequency Fourier modes, and that produces a characteristic signature in the Fourier domain. So everything I've told you and more, the theory, started in this paper with Michael Johnson, who is now the PI on the NASA mission that will go to space and measure this photon ring, Andy Strometer, who's my advisor. And we also wrote papers with Sam Gralla at the University of Arizona that rigorously prove everything I told you. So these are the references if you want to check that out. And before I move to the experimental side, I want to mention one key connection for people here, because I know there's a lot of gravitational wave scientists. So this is a plot that has nothing to do with black hole imaging. This is the famous LIGO detection, the first one from 2016. And what you see is the gravitational waveform for the merger of two black holes. And it has three phases. There's a slow oscillation, which is the in-spiral phase, when the black holes are slowly orbiting each other. Then at some point, they actually coalesce. It's the black hole merger, and that's a nonlinear phase for which we really need numerical simulations to describe. And then once you have a single black hole, it rapidly settles back down to equilibrium by ringing, by emitting radiation via these exponentially damped quasi-normal modes, which are the characteristic nodes of the black hole, and that's these damped oscillations that exponentially go to 0. So this is a movie of what I just said in words. So this is the thing that happens in space-time that produces those gravitational waveforms that LIGO saw. So you have two black holes orbiting around each other. It's going to happen very, very fast. But pretty soon they're going to merge. And then once they merge, there's going to be a single black hole, which is going to rapidly settle down to equilibrium by emitting gravitational radiation. Okay, it's happening now, single black hole. And I want you to look here. I'm going to play this again while I talk. So it turns out that the last part of the gravitational waveform that you see is the last gravitational radiation to be emitted from the system. And the last gravitational radiation to leak out from the region around the black hole is the radiation that you can think of as gravitons now that orbited around the photon shell before escaping. So we called it the photon ring, but you could also have called it the graviton ring. You can see it here. The last ripples of space-time that leak out after a merger, producing this quasi-normal mode ringing, are actually connected to the photon ring. And this correspondence was known in the 80s for Schwarzschild, and it was only worked out a couple of years ago for Kerr, which is very surprising, actually. And I can actually give you an exact explicit expression for the quasi-normal mode spectrum. So this is omega LMN. These are a set of frequencies that describe the exponential ringing of the black hole as it settles to equilibrium. So you can think of them as the characteristic notes of a black hole. When you ring a bell, you can look at its normal modes that are fixed by the geometry and structure of the bell, and that tells you the characteristic sound of the bell. And if you have a black hole, you can, because you know its geometry, it's the Kerr geometry, you can ask when you ring it or perturb it, what are its characteristic notes? So they're predicted by the Kerr geometry, but they're very hard to compute, and there is no analytic formula for them, except in the regime of high frequency, where you can describe them by this formula. So these notes have three integers that label them, L, M, and N. L and M are like spherical harmonics, but they start at L equals 2 because gravity has spin 2. M can range from minus L to plus L. It's the usual spherical harmonics business. And N is an overtone number. So N equals 0 is the fundamental note. And then you have these higher frequencies that are labeled by positive N. And a large frequency, omega, or equivalently large harmonic number L, you can compute this analytic approximation to the spectrum in a series expansion in 1 over L. So in leading order, you have this leading linear piece in L with a real coefficient omega r. And then at subleading order, which is constant in L, you have an imaginary piece, minus I times n plus a half, times another function, gamma L. And the really cool thing about this is that knowing the spectrum of quasi-normal modes, so the characteristic notes of the black hole in this regime, is equivalent to knowing these two functions, omega r and gamma L. They depend on M and L. And here's how you compute them. M goes from minus L to plus L. So M over L is between minus 1 and 1. And if L is very large, actually M over L is almost a continuous parameter that goes from -1 to 1. And I gave you such a parameter 20 minutes ago. It was mu. So for every m over L, you can associate an inclination, sine theta, and therefore a photon shell radius, which is the orbital radius in the photon shell where the photons bounce up and down up until this inclination theta, which is related to m over L by this relation. So there's a one-to-one correspondence between m over L and r. And it turns out that these coefficients that describe the notes of the black hole are actually computed by the critical exponents of the photon ring that I described. So for instance, this imaginary piece is called the Lyapunov exponent gamma L. It's different from the one I mentioned before, but it's basically the orbital Lyapunov exponent of the associated bound orbit divided by its half period. Yes? Well, okay, maybe let me use a different word then. I don't know, it's a bit of a philosophical question. So what I would say is, when you have high-frequency quasi-normal modes, because they're high-frequency, you can think of them as wavefronts of geodesics. That's the so-called iconal approximation. And so the iconal quasi-normal modes, the part of the spectrum that has high frequency, can be thought of as photons traveling around the background. Whether it's gravity or photons is subleading at this order, it doesn't matter. And the waves that correspond to quasi-normal modes, the boundary conditions that you impose on them to obtain quasi-normal modes, actually force the photons to be described by bound orbits. And that makes sense, because the quasi-normal mode signal is the stuff that leaks out very slowly at late times. And the last radiation that you get is the one that tumbled around the photon shell for a long time before leaking out. So yeah, related to is certainly correct. But I wanted to give it more force because the parameters of the photon shell dictate the form of the spectrum in this regime. And I should say that LIGO and LISA will measure the low-lying level modes, which are L equals 2 and L equals 3, hopefully. And this approximation is correct about 10% by the time you're at L equals 3, and it's basically perfect by the time you're at L equals 4. So it's not useful for LIGO and LISA, really, but it describes sort of the opposite regime of high L that we can't probe with gravitational waves. So this is a sort of a complementary window into a different part of the black hole quasi-normal mode spectrum. Okay, and now the last slide I want to say is about an experimental proposal to measure this with Sam Gralla and Dan Moroni. The details are in here. But here's all you need to understand. This is an image of a black hole where we turned off strong lensing. So there's just a disk, and we're not seeing orbiting light, so there's no photon ring. And then this is the same image where we now allow light rays to orbit around the black hole, and so we get the multiple images that produce the photon ring. Okay? And these are images, but what interferometers observe is the radiovisibility, which is a complex quantity that is just the Fourier transform of the image. And you can take its amplitude, so the modulus of this complex thing, and you can look at it along rays in the Fourier plane. If that was a little too fast, don't worry about it. This is basically the response in the interferometer. And the point I want to make is that if you have a thick ring, what you get are a few hops, but the signal gets resolved out very fast. And if you have a very, very thin ring, because there's rapid variation in the image, there's large gradients, you get high frequency Fourier modes, and so you have power on much longer frequencies, which correspond to larger separations between the telescopes. So the x-axis here is the baseline, which you should think of as the distance between the telescopes in your interferometric array. And then the y-axis is the visibility, which is the response in the interferometer. And if you have a thick ring, and you take your telescopes to be very far apart, basically you see nothing, because you resolve out the source. But if your ring is very, very thin, then even a large separation, you're going to see a ringing, which is produced by the ring. And you can show analytically that the period of this ringing response is set by the diameter of this ring. So this is the big vision for the experiment. This is the Earth. This is the line of sight to M87. We're going to put a satellite in orbit around the Earth, roughly in a plane perpendicular to the line of sight to M87. as the satellite goes around the Earth at every angle phi around its orbit, it's going to measure this kind of interferometric response with a characteristic ringing or periodicity. And that periodicity actually encodes the diameter of the ring, d phi, at the corresponding angle phi around the image. So this angle phi is the same as this one. And this is a little confusing because this is an image angle phi and this is an orbital angle phi, which lives in the Fourier domain. But anyway, it's not obvious at all, but it works out in this beautiful, intricate way that you only need one satellite orbiting around the Earth to measure the shape of the ring at every angle. Because as the satellite orbits around the Earth, it can measure the diameter of the ring at one angle, and then as you go around the orbit, you get all angles. So we're going to put a dish in space. We're going to have one or more on Earth. And we're going to sample the baselines that are long enough that sit around here, which is just long enough to tell, no signal, no photon ring, or clear ringing signal, there is a photon ring. So we're going to detect the ring. And we're not just going to detect it, but by having the satellite go around and averaging over many observations, we're going to measure its angle we're going to measure its diameter at every angle. And this is, again, not obvious at all, but it turns out there's a prediction for the shape of this ring. This diameter is a function of angle from the Kerr geometry, which is that it has to take this functional form. Now, what R0, R1, and R2 are, I can't tell you. That depends on the black hole parameters, and also, to some extent, on the details of the emission around the black hole. But roughly, R0 sets the scale of the ring, so it's related to the mass. And then R1 and R2 are the ellipticity, which is related to the spin. And this could be a whole other talk, but by measuring this, we'll be able to infer black hole mass and spin with very high precision. All right, so now I'm over time. I'll just flash some pictures. We had a meeting last fall at NASA Goddard, which is the major space flight center in the United States. They're very excited about this mission. It's called the Black Hole Explorer, or BHEX. There's some technical details here of what we're going to be able to do by connecting the satellite in space to the Earth. We'll go from low resolution to high resolution. This is the kind of interferometric data that we think we'll be able to get, and the kinds of spin measurements that we'll be able to do. There's a bunch of details that I can talk about. All you need to care about is that if the source really looks like this is what we can see with the Event Horizon Telescope, which is blurry because it's limited by the diameter of the Earth. That sets a maximal distance between telescopes. But by having an additional telescope in space, we'll be able to get this kind of observation, and we'll be able to make movies too. So in the next 10, 15 years, expect to see actual movies of black holes that kind of look like this. And yeah, I should say I'm very excited about this. The proposal is due in May next year, and we'll know by the end of next year officially if this goes through. If it's selected, this will fly in 2031. And we've had excellent feedback so far, so I'm very hopeful that this is going to happen, and I'm happy to hang out and take more questions. Thank you for your time.
Okay, thanks, Alex. I think we had a lot of questions, but maybe if there's some urgent, quick questions in the audience, go ahead. Yeah.
Is there any hope with the Black Hole Explorer to see not only N=1 photon ring, but also smaller rings?
If you could repeat the question.
Yeah, so the question is there any hope of seeing not just N=1, but N=2, the higher order photon rings with Black Hole Explorer? And the answer is no. And there's a plot that I have that explains this. So just like whatever the N=0 image is, it depends on the astrophysics of the source, but once you have that, the pattern of lensed images is fixed by GR. The same universal structure, where universal means independent of astrophysics, but fixed only by the geometry, also exists in the Fourier domain that the interferometer probes, where now the rings basically produce signals that die off at large telescope separations. So if the ring has a width W, once the separation between the telescopes is of order 1/W, you can resolve its width, and then its power exponentially dies off. So once you get large enough separation, the N=0 signal dies, but then the N=1 ring is much thinner, so then it starts to dominate the signal. You get this, and then once you have enough precision to resolve the width of the n equals 1 ring, then its signal dies off, but the n equals 2 is still unresolved, and its signal takes over. So basically, you can think of having two telescopes and varying the distance between them, which is moving along the scale here on the x-axis. And where you position your telescopes basically tunes which photon ring dominates the signal. And by going to these kinds of orbits, so of course, the x-axis is the separation between the telescopes measured in units of the observation wavelength. It's a dimensionless parameter. So you can also play with the observation frequency, but that's a very complicated game. With BHEX, we're going to improve by 50% the frequency relative to the HD. So this is the HD observing frequency, 230 gigahertz or 1.3 millimeters. BHEX is going to go down to 0.8 millimeters or 340 gigahertz. So that's about here. This length here is the Earth diameter. But we're going to go to MEO. So we're going to be smack in n equals 1 territory. And if you wanted to see n equals 2, you would have those frequencies, which is all we can realistically access within the next 15 years. Then you have to go to the moon. So if BHEX flies in 2031 and we see the n equals 1 photon ring, we'll propose BHEX 2, which will be to put a satellite in orbit at lunar distance, or maybe around the moon. And that would be perfectly tuned to resolve out the n equals 1 ring and see only the n equals 2. And because we're very bullish about our chances of success now, there's even discussion of pre-planning for this and making the BHEX 1 satellite tuned for n equals 1 have the capability to, in the future, connect to another satellite in space. And the reason we're limited in frequency really comes down to our atmosphere, which is very difficult to see through as you vary the frequency. And so, you know, the future of this eventually will be pure space VLBI, where all your telescopes are in space, kind of like LISA, but we're far away from that. No, we're not going to talk about that for 20 years, I think. Yeah. Yeah, so yeah, I can talk to you about that for an hour. So the reason, okay, so actually, BHEX, first of all, the orbit is not optimized yet. There are people at NASA who are dynamicists, and they're optimizing orbits full time, like that's their job, and they're still twiddling this. There's a nice orbit which is geo-locked. It's a 12-hour orbit, so you pass over the same region over the Earth twice per day, and that's useful for downlinking the data that the satellite observes, because we need ground stations to receive that. So there's a lot of engineering constraints. The scientific constraint is that for M87, we really want to measure the diameter at every angle, which means we need to be roughly at the same distance in the baseline plane. So we want the orbit for M87 to be circular in the plane perpendicular to M87. But if you do that, Sagittarius star is basically at almost 90 degrees. So for the plane perpendicular to the line of sight to Sagittarius star, we are actually highly eccentric. And for very complicated astrophysical reasons, that's actually really good, because for Sagittarius star, we're looking through the galactic plane. And so the light doesn't propagate freely, but scatters through the interstellar medium. There's a scattering kernel, and it's anisotropic. So depending on what position the satellite is in, you can see deeper or not to the source. And so there's a highly fine-tuned orbit that is circular for M87, which lets you see the diameter at every angle and enables you to carry out this test and measure black hole mass and spin. And that same orbit is highly eccentric relative to Sagittarius star with just the right orientation to take advantage of the anisotropy in its scattering kernel. And you know, like these are words that I don't think I could have said a year ago, but once you get into, you know, what I told you was like simple calculations theory, but once you get into the details of optimizing orbits and measurements, it gets very, very complicated very fast.
Okay,
Yeah.
maybe a last question.
Well, this is like Johnny's question. It's a little bit in the eye of the beholder. I think there's no quantum gravity in any of the observations we're going to make. Actually, there was this question I got once about, how is this not quantum gravity because the photon rings are indexed by n, so there's quantization. I just want to make it clear, there's no quantum mechanics in here. In fact, we don't even need to care about the wave nature of light. So everything I told you about was assuming that photons are point particles, which assumes the geometric optics approximation. And that's a very good approximation here, because I told you that M87 is a black hole that's bigger than our solar system, and the wavelength of the photons we're measuring is about 1 millimeter. So you can expand in the wavelength relative to the radius of curvature. It's 1 millimeter divided by the size of the solar system. That's a very small parameter. So basically, we don't even care that the light is a wave, and quantum effects just don't matter at all. Yeah, that's true. Yeah, but for the purpose of describing what's going on, up until the interferometer, we can ignore the wave nature of light. So basically, there is no quantum mechanics involved anywhere. We're also not going to see Hawking radiation. These black holes have a temperature of about 10 to the minus 17 Kelvin, which you can estimate based on their mass. And the hot gas around them is about 10 to the 11 Kelvin. So, you're not going to measure Hawking radiation. So yeah, there's no quantum mechanics. Now, I should say, I think it is a classical probe of gravity in the strong field regime, because only this extreme gravitational field can lens light so much that you get a photon ring. So just qualitatively observing a photon ring means that there's orbiting light, means there's a strong gravitational field, and then precision measurements of the photon ring and its structure give you precision probes of the Kerr geometry. And for high energy theorists, that sounds maybe not that exciting, but I should say that, from an astrophysics perspective, the Kerr hypothesis has not really been tested to high precision. LIGO has tests to the 4% level, and they're going to get much better. But again, that's stellar-sized black holes in the dynamical regime. Here we're going to probe supermassive black holes in the static regime of pristine gravity. It's just a different window. And we're going to also get very high precision measurements. And we're going to be able to test the Kerr hypothesis, which is good science, because it's an assumption that is the workhorse assumption today in astrophysics. It underlies all of our models. And it's just good science to test it. So I think we're going to find out that it's a Kerr black hole probably, but the place where I think it's interesting for high energy theorists is that actually just thinking about black hole images has changed the way that many of us, certainly myself, think about black holes. And there have been papers on holographic connections, as you well know, which I think were prompted by some of the observations I discussed today that we would not have thought of otherwise. And I think being in conversation with experiments is a very healthy thing. It changes the way you think. Okay, and on that note, we're way over time, but I'm here today and tomorrow, and I have a lot of energy. So just come hang out and ask questions if you want. Thank you for your time.
All right, thanks again, Max. We're taking him out for a speaker dinner, so if you're interested in joining, let me know really soon so I can book.